Yeah, recording started, sir.
Good evening all. Myself J. Arul Prakash, Assistant Professor, Department of EEE, Jerusalem College of Engineering. I welcome you all for the second day of 1 week online FDP on electric vehicle drive system. I extend my heartful welcome to today's speaker, Dr. M. Balaji, Associate Professor, Department of EEE, SSN College of Engineering. It's my privilege to introduce that to the audience. Dr. M. Balaji, Associate Professor in the Department of Electrical and Electronics Engineering. He is having a teaching experience of around 15 years, including research. He received his BE EEE degree first class with the distinction from Annamalai University. He secured a fifth university rank for the ME Powertronics and Drives from Sri Venkateswara College of Engineering, Anna University, and PhD in the area of special electrical machines from Anna University. He has published 25 papers in international journal and around 40 papers in national and international conferences. He has coordinated an international conferences, organized national level workshops, and has delivered guest lectures at various conferences and workshops. He is a recognized supervisor for Anna University. He is currently guiding 5 PhD scholars and 4 scholars have completed PhD under his guidance. His area of interest includes design and control aspects of electrical machines, electric vehicles, and power converters. He has completed a SAFE project titled Design and Development of Hybrid Switch Reluctance Motor worth rupees 22.9 lakhs under Fast Track Scheme for Young Scientists during the year 2015 to 2018. He is the co-principal investigator for the project titled Design and Development of a Permanent Magnet Assistant Reluctance Motor Drive for Pump Application, funded by SUB worth rupees 21 lakh 18,978. So, I welcome you, sir.
Thank you. Thank you, Arul. First of all, I'd like to thank the management of Jerusalem College of Engineering for inviting me to give this lecture. I'd also like to thank Dr. Vinod, Rudra ma'am, Arul sir for inviting me for this workshop, 1 week faculty development program. Right. Hope my audio and PPT are visible.
Yes, sir, it's visible, sir.
Okay. Okay. So, good evening to all learned participants. So, I thought I'd share some of the aspects of fault diagnosis of electrical motor drives. So, today we speak a lot about electric vehicles and what are the components of electric vehicles, the power electronics for electric vehicles. So, that is how the workshop is organized. So, if you see, the yesterday's session was about the introduction for electric vehicles, and the remaining speakers in this week they'll talk about various challenges, the power converter topologies. So like that, the organization of the workshop is there. So today I thought I'd focus on the possibilities of fault diagnosis and where you can contribute in this electric vehicle research, because this is one of the areas wherein the so-called machine learning approaches, the computer science based approaches can be applied, and we can go for interdisciplinary research combining the mechanical aspects, electrical aspects, and computer science related machine learning algorithms can be integrated, and we can develop newer control strategies or control algorithms for detecting the fault in electric motor drives. So that is the objective of my research work, objective of this particular speech, and hope you can take this forward and pursue your research, or you can publish some papers regarding this. So that is how I have planned this particular lecture. So this is the outline of my presentation. So what are the classification of electrical machines which is widely used in industry? What are the different kinds of faults that can occur in electrical machines? So not as electrical machines, I take it as a generally a drive as a whole, and how to diagnose the fault. And I thought of presenting some case studies in BLDC motors, SRM motors, and how machine learning can be applied for fault diagnosis. This is widely being explored now, as I said earlier, how machine learning can be incorporated for diagnosing the fault in EV. Okay, since the workshop is related to EV, you can apply it for electrical vehicle or in general for any application, whatever application wherein you employ drive. Okay, this sort of principles can be applied. It's not only restricted for EV. Right. So this is the outline of my presentation. So first, I'd like to again summarize the structure of the electric vehicle. So this is the main structure of electric vehicle that is being exposed. So the main component of EV, if you take, is the battery pack, or you take, this is the battery pack. So and then we'll have the power electronics. We'll have this AC DC converter, or we, depending upon the type of motor, we go for different converter topologies. Okay, generally, predominantly, we prefer DC to AC inverter or DC DC converter. This DC DC converter is used for multiple purpose. Okay, it can be a bidirectional one, or here, okay, in this work, what they have presented is they are giving some
Slide is
excitation.
not moving, sir. Actually,
Uh,
sorry, sir. Sorry to
okay,
interrupt you.
is it moving?
No, sir. Still, the first slide is just only there in the screen.
1 minute.
Yes, sir. It's now visible.
It is now visible. Okay.
Yes, sir.
Okay. So this is the outline of my presentation: classification of electrical machines, what are the faults, and how to diagnose the fault, and some case studies. So if you take the general structure, okay, if you take the structure of electric vehicles, so we have the important aspect to be the battery pack. So this is the first thing. So from the battery, okay, the electrical motor is powered through a power electronic interface, and then we employ DC DC converter. Either we can be use it, it can be used for regenerative braking, or here what in this work what they have mentioned is they are providing some sort of excitation to the motor, uh, maybe a synchronous motor. Okay, so that is one idea wherein they have used, or we can use it for regenerative braking or different purpose. So your power electronics comes into picture, and then your electrical motor comes into picture. And these two are very important aspects. One is the vehicle controller, wherein the entire operation of the vehicle is controlled, and then the energy management unit. Okay, what is the charge that is present, whether the battery has to be recharged, or the entire energy management, okay, will be controlled, and as well as vehicle controller, okay, which takes care of vehicle dynamics, which take care of the feedback from the different sensors, and it provides the corresponding firing pulses for your converter and inverter as well. So this is the overall structure of your electric vehicle. So now when you see this overall structure, this structure this is what will be deliberated in the FDP program. Okay, all the aspects of the electric vehicle. So now when you take this electric vehicle structure, okay, it is prone to fault in different regions. Okay, different regions in the sense, okay, the battery has to be monitored. That is the first thing. The power electronics has to be monitored. That is the second thing. And the electrical motor has to be monitored. So that is where exactly I thought I'd throw some light for the young people to work upon and take up this as a research issue. Okay. So it is prone to fault. So every aspect is very important. Okay. The mechanical transmission is also important. The electrical part is also important. The power electronics part and the battery part. Okay. Or I can say the energy source is also important. So all these aspects play a very important role. And so when you take the faults, see here, this is a pictorial representation, okay, of just the power electronic component, right? So when you see the fault, for just for example, I have taken this, the fault can occur anywhere here. So what we can consider is the fault can occur first in the capacitor. So here Okay, there might be a short circuit here. So that is what is a big test. So this is one kind of fault. Or the switch can be a open circuit fault or short circuit fault. Or a diode can be of fault. Or there can be a fault in this chopper. So here they have used as a synchronous motor, just a representation, right? Or the winding fault. So see here, there are different areas in which the failure can occur. Okay, first one, your capacitor fault. Second one is your device fault or your winding fault or your power electronics fault. So there are different instances where the fault can occur, and it is very important to identify the nature of fault. There are two important things. First, how will you provide a solution? First, you need to identify the fault. Okay, first you need to identify the fault, and then second one is to provide solution for this. There are two aspects of it. So that is what we call it as diagnosis. Okay, first we need to diagnose. Why we need to diagnose? We need to diagnose and find out what is the type of fault, or identify the type of fault, and then we should provide solution. So what is the solution? Either we can stop the vehicle, or we can isolate this, right? Or we can have an alternate arm. Like this, we need to provide solution for the different types of faults that are occurring. So this is very important aspect. And how are we going to identify the fault is a very important aspect. And how are we going to provide solution to the fault is again another aspect. So this is when you take the vehicle as a whole, right, you require a lot of sensors for this. And how will you sensors, and a lot of data is required. So that is where machine learning approaches are very much utilized in this particular aspect. So we need to have large number of data. Why? You need to have a sensor. From the sensor, you need to have the voltage value, you need to have the current value. Okay, you need to have the mechanical vibration aspects, you need to have the thermal aspects. So all these aspects, okay, all these aspects you need to monitor, and based on these values you need to take the corrective action. So that is why they prefer since it is, I call it as a data based approach. Okay, this is called as a data approach or data based approach. Okay, so this machine learning comes into picture, or you can call it as data analytics also as well. So large number of data is involved, large number of sensors is also involved to make the vehicle very smart, I can say, make the vehicle very smart, and for detecting the fault. So that is where we are going to concentrate in this particular session. So this is one important thing, okay, wherein we call it as battery management system. So when you take the battery management system, just a block diagram, see what we need to monitor. We'll monitor the current, we'll monitor the temperature, voltage. How we'll monitor? We'll monitor it through the sensors. So the sensors will again give it to a temperature management system. So temperature management system will regulate the cooling of the battery pack. This is one aspect. Similarly, the values has to interface with the energy management system, and it will provide what is the corrective action that needs to be required. Okay, whether we need to charge it, or whether what is the charge that is left, whether the vehicle can move or not, whether there is a fault in the cell, like this, all these things it will be informing. So energy management is again coupled to two aspects, one to the load, other to the charging equipment. And see here, all these things, okay, the sensors again interact with the safety management. The energy management again move with data communication, and vehicle control unit will also go with data communication. And what we tend to do again, we estimate the state of the vehicle or state of the movement of the vehicle, and then we go for a fault diagnosis algorithm, and based on the fault diagnosis algorithm, the safety management system will take a critical action. So this is just to inform you that in a battery management system itself, there are a lot of process that is involved, and we need to monitor the data. Okay, so that is what I said. It is basically a data-driven approach. It is basically a data-driven approach. We require a lot of data for two cases. Okay, how will you identify it is a fault? First, we need to know what is the value under ideal condition, what is the value under fault condition. So only then we'll be able to identify the fault. So this is for a battery management system. I am talking about battery management alone. See, there is a lot of things that is involved in battery management system as well. So this is one aspect. Similarly, when you take the drive aspect, so there is again certain challenges there. So that is what we need to understand. So this is rough an introduction of why this fault diagnosis is very important. And when you take the classification of electrical motors, and we can classify the motors as AC motors and DC motors, and predominantly in electric vehicles, we tend to use permanent magnet machines, permanent magnet PMSM or BLDC, because it is The size is very less. It is compact and high torque. Or some also use induction motors. Some company also use induction motors, right? So these are predominantly used machines. And since these PMSM and BLDCs involved permanent magnets, which is made up of NdFeB, neodymium freon boron, some companies are also looking for switch reluctance motors for building electric vehicles, for motors for electric vehicles. Okay, I'm sure one of these sessions, Prabhu will also be interacting on how to design permanent magnet motors for EV applications, right? And tomorrow, I think Dr. Jayaprakash sir will also discuss upon how to design an SR machine for electric vehicle application. So each and every machine has its own advantages and disadvantages, but overall we can apply all these machines for electric vehicles. And uh, we can understand that all these machines have emanated from a basic topology of synchronous machines. From synchronous machines only, all these topologies, the brushless DC motor or PMSM motor or reluctance motor, all these machines have emanated from the synchronous motor topologies. And please understand, for fault diagnosis, each motor is different. The operation of each and every motor is different. The power converter that is required for the motor is different. So the fault diagnosis strategy will be different. Fault diagnosis strategy will be different. So we need to choose the motor, choose the converter, and then only we can design a controller for it. Because when you take a switch reluctance motor, there are a lot of converter topologies available. Similarly, brushless DC motor, we can go for a conventional inverter or we can go for a multi-level inverter. Like that, we can go. So likewise, the control aspect as well involves a lot of strategies and lot of converter topologies. Lot of converter topologies are also present. Okay, or we can also have a front-end DC converter topology as well. So likewise, since we have a larger number of variations, right? So each configuration of EV will be different. Okay, so that is basically a challenge. So what structure we are going to take and how we are going to diagnose the fault is different. So that is where there is a challenge and that is where there is a scope to work. So I like to highlight the point that each and every motor has a different topology, design wise, converter wise, and control strategy wise. So whenever I deal a fault diagnosis algorithm, okay, it is not specific. It cannot be combined. It cannot be used for the entire EV train. So whatever topology I'm going to use, I need to adapt it. I need to change it according to the motor that I'm going to use, converter that I'm going to use. Like this, I need to adapt it. So each and every algorithm will be different. So again, this offers a lot of scope for us to work, to take up a converter topology and proceed with the fault diagnosis for that particular converter topology. So likewise, we can expand our scope of work in this particular area. So this is the classification of electric motors. Okay, and generally when you take the classification of electric motors and faults, okay, so generally we have state faults in electrical motors can be classified as stator related faults. Okay, the winding fault or the bearing fault, like the rotor bearing will be faults. So rotor related faults, okay, you can classify it. Or we can have bearing faults, it is separate. And we can have eccentricity related fault. So when you take an electrical machine, okay, electrical motor, generally it's a general diagrammatic representation. We can have stator related fault, we can have bearing fault, or we can have rotor related fault, we can have eccentricity related fault. Okay, because rotor also employs permanent magnet, there is a possibility of faults in the rotor as well. And bearing fault is separate. Stator related fault, since it employs winding, there might be winding open circuit, short circuit, so those aspects will be there. And eccentricity related fault, okay, will also be present. So it can occur at any instant of time. So all these things needs to be analyzed and a fault diagnosis algorithm needs to be developed. So, and so far I have taken all these things from this particular reference paper, fault diagnosis method and fault tolerant control strategies. So see the fault cause, okay, this paper has you beautifully mentioned, it can be because of thermal aging. Thermal overloading can cause different type of fault. It can be because of electric over voltage, electrical discharges, or dielectric aging, or lamination. Okay, rotor strikes the stator, corrosion, leakage in cooling system, improper lubrication, centrifugal forces acting on it, poor installation of or fabrication. So these are all the different causes of fault. and these faults can cause the different faults. Okay, these are the causes of fault, and these are all the faults. It can be winding short circuit, winding open circuit, bearing damage, bent shaft, rotor to stator misalignment, eccentricity, dynamic air gap, semiconductor faults, semiconductor short circuit fault, DC link short circuit fault. Sensor disconnection is very important because most of the special electrical machines will employ rotor position sensors. Okay, or they also go for sensorless control. They also go for sensorless control. But if they employ encoder type of thing, then the sensor fault is very important. Okay, so likewise, there are different fault modes, and what are the effects? Okay, the effects are reduced torque, vibration, noise, eccentricity, increased losses. Vibration will cause torque pulsations. Okay, increased ripple voltage, closed loop control failure, control effect reduced. So all these are effects of fault. So this slide will summarize what are the causes of fault, why the fault is caused. Okay, why the fault is caused. When the fault is caused, what will happen? Okay, because of this fault, what will happen? The winding gates will get short circuited, and because of this, what will be the performance of the machine? So what will be the performance of the machine? The performance of the machine will be deteriorated. So these are all the fault effects. So now why fault diagnosis is very important? Why fault diagnosis is very important? Because there is a possibility that there can be all these faults, and all these faults, what it will do, it will reduce the performance of the machine, it will reduce the performance of the machine, and it will reduce the safety aspects of the machine as well. So that is why we need to go for a fault diagnosis approach, fault diagnosis, fault detection, and we need to provide solution. So that is the main reason why we need to go for fault diagnosis. So this is the reason that researchers are working in this particular area, right? So what are this is what again I have summarized a few points. Effects of fault: it can be unbalanced voltages, increased torque pulsations, decreased average torque, increased losses, excessive heating, and safety aspects as well. Okay, safety aspects as well needs to be considered. So these are all the effects of faults in electrical machines, and we need to diagnose this. So how are we going to do that? So how are we going to do it? So that is what we call it as condition monitoring, or we call it as predictive maintenance. So what is predictive maintenance? We measure the signal. What signal we are going to measure? We measure what are the signals that we can measure? We can measure the voltage signal. We can measure the current signal. We can measure the vibration signal. We can measure the thermal aspects. Okay, all these signals we are going to measure. And we are going to see if there is a fault or not. Okay, based on a threshold. Okay, we'll have a threshold for ideal case. Okay, we'll have a threshold for an ideal case. Based on the threshold, we'll see whether there is a fault or not. If there is a fault, what we'll do, we'll diagnose the fault, we'll analyze the fault, and we will take an action. Okay, this action can be change the speed, or stop the vehicle, or charging. Okay, like this there can be different actions that can be performed, or switch on an alternate switch. Like this there can be a different actions which can be taken. So this diagram summarizes the entire process. Okay, entire process of fault diagnosis. And from this diagram we know that the very important aspect in fault diagnosis is we need to measure the signals. We need to analyze the signals. We need to analyze the signals. Okay, analysis of signals is very important. Signal analysis. Because for different type of fault, the variation will be different. You measure the current. For open circuit fault, the value will be different. For short circuit fault, the value will be different. If there is any other fault, okay, if there is encoder fault, the value will be different. So like this, for different types of fault, the sensor values, okay, the output signal values will change. So when the output signal values changes, okay, what will happen? We need to monitor it. Okay, that is what we need. We call it as condition monitoring system. So first, for that, what we need to do, we need to have a data under ideal condition. What is the value? So when there is a open circuit fault, what is the value of current? When there is a short circuit fault, what is the value of current? So like this, I can I need to prepare a database that predicts or that has the ideal value, and that has the fault values. Only if I have a database, then I can distinguish between an ideal condition and a faulty condition. So that is where data analytics plays a very important role. So this is how it is done. And as I said, the motor fault type can be classified into mechanical fault and electrical fault. And how do we diagnose the fault? How are we going to diagnose the fault? So for diagnosing the fault, we have two techniques. Okay, one, we have a sensor based approach. Okay, that is this also employs sensor. One we call it as non-invasive techniques, and other we call it as invasive techniques. So in invasive techniques, okay, what happens is I employ specific sensors. I mount the sensors on the motor for predicting the noise, for predicting the thermal effects, for predicting the sound, okay, or if say, there is battery, I do some chemical analysis, or for predicting the vibration. So what is it? I use some sensors for diagnosing the fault. In non-invasive techniques, okay, I'll employ current sensors for closed loop control. So from that itself, I'll analyze and see whether there is a fault or not. So there are two approaches in fault diagnosis. One, it is a sensor based approach. Other, I call it as a not. This also employs sensors, but not physical sensors are mounted, okay, as to estimate the noise, thermal, and all those things. So there are two techniques: invasive techniques and non-invasive techniques. Okay. And what are the methods? Okay, what are the methods? This is what I said. So fault detection, okay, I have model free method, or I can go for model based method. So there are two things, okay, which I can go. Okay, one, I call it as a model free method. So how am I going to detect the fault? Okay, one I call it as a model free method and a model based method. So model free method, okay, it is again what we call it as a signal based method. Okay, I use the sensors and measure it. Or model based method, I'll have a parallel model which is running, okay, which is similar to the actual model. Based on that, I'll have a model based approach. And then in fault diagnosis, I have two approaches. One, I call it as a classification method. I call it as reasoning method. Right? Reasoning method in the sense, if this value is greater than this value, then the fault is this category. If the current exceeds 20 amperes, so then we have a fault, short circuit fault. If the voltage is within this particular value, then there might be a short circuit fault. So like this, I can have classification methods. Okay, again, I have a data, I'll train it, and then I can classify what is the nature of fault. So this require a lot of database. But this is basically reasoning. Okay, I predict the value, and from that I'll have the output. So this is what I call it as model based. In a model based approach, what will happen? I'll have the original machine. Okay, I'll have the model. Both will be running in parallel. Okay, and then based on the output, I'll give the same input. Okay, this model will predict the correct output. In case of fault, what will happen? The observed output will vary. And based on the comparison between the predicted output and observed output, what will happen? I can make a decision. I'll repeat it. So in a model based approach, I'll have a model which is similar to the plant which is running. I'll give the actual input to the plant or the drive as well as the model. This model will produce the correct output. I can say it will produce the correct output. Okay, I do have tuned it to the actual output. And then I'll have this plant. Okay, this will give the actual output. So based on the difference between the correct output and the actual output, or I can call it as a reference output and the actual output, what I can do is I can make a decision what type of fault. Okay, so this is one approach which I can do it. Okay, so this is what I call it as model based fault diagnosis. So what are the different methods here? So here again we have two things. One, we call it as a qualitative model and quantitative model. So here we have knowledge based trend analysis and hierarchy. Okay, we can have different hierarchy based models, or here I can have a parameter estimation. I estimate the parameter. I go for computational intelligence method, or I go for quality control based method. So these are all the model based fault detection methods. Right. Similar approach can also be followed for power devices as well. As I have dealt earlier, in power devices, there can be fault in capacitance, in IGBT, or in diode. Okay, so the similar approach can be followed for power devices as well. So here again, in a semiconductor fault diagnostic algorithm, I have signal based approach, I have model based approach. Okay, here signal based approach, because all these values are time varying. Okay, all these values are time varying. Now what do you mean by time varying? In time varying, we do not know where the fault will occur. So naturally, when I start the vehicle and when it is running, the current will be like this. When there is a fault, what will happen? There will be a variation. Either it can go high or low. Okay, like this, the time or instant of occurrence of fault can be anywhere. So that is the major challenge. So all these electrical quantities are time varying quantities, or time varying quantities. So that is why it is going to be a real challenge. Okay. So these are all the different types of fault. This I have already dealt. Okay, you can have a short circuit fault, you can have an open circuit fault, you can have eccentricity fault, bearing fault, magnetization fault, like this. These are all the different faults in PMSM, PM machines. Okay, so this is what I said. So in non-invasive method, what I can do is I get the signals. Okay, I get the signals. Okay, it's not that I'm not going to use any sensors. I'll use sensors, but for voltage and current. I'll condition the signals. I'll sample the data, and based on the signals, I'll extract the features. Okay, why feature extraction is very important is I need to know what is the type of fault, because the pattern for different type of faults will be varying. So from the pattern, I should extract the features. Okay, from the features, I'll tend to classify the fault, or I'll go for decision making algorithms. Okay, so that is why this feature extraction stage is very important. This feature extraction stage becomes very important. So this is what I call it as a non-invasive technique. So in non-invasive technique, okay, what I do is I'll take the voltages and currents, I'll filter it out, filter and get the original values. Okay, and I'll extract the features and I'll classify the fault. Okay, later on when I give some example, you will be able to understand, okay, why feature extraction is very much required. Right, in invasive method, what I do, again the same thing, I go for some vibration signals. Here I mount the sensors. Okay, here I mount the sensors. So from the sensors, what I tend to do is I tend to segment the values. I'll extract the features. Both follow the same features. Okay, same steps, right? But here I'll have extra sensors for measuring the vibration. So there, what will I do is I'll, with the help of current and voltage sensors itself, so I'll extract the features, and then I'll normalize it, and then I'll classify it whether there is a, I'll classify whether there is a fault or not. So that is how it is done, right? So from the vibration signals, I'll extract the features. So from the features, I'll classify the fault. Okay, I'll classify the. So that is what is in the case of invasive method, right? Okay, so what are the steps? The steps are I need to collect the data. Either it can be a invasive method or non-invasive method. I should collect the data. I should extract the features. From the features, I'll classify whether there is a fault or not. So these are the steps to be followed, right? And why signal processing is very important? Because as I said, all these signals, okay, all these voltage signals, current signals, and vibration signals are time varying. So that is why I'll go for time frequency transformation for extracting the features. Time frequency transformation for feature extraction. For feature extraction, right? So in time frequency transformation, there are different techniques. I am not going into the details, right? So once we extract the features, then we can identify the fault, right? We can identify the fault with the help of neural network, with the help of fuzzy logic algorithms, expert systems, or we can use hybrid AI techniques for identification and classification of the faults. So this is how it is done, right? So with this, I'll give a short break. Okay, any feedback or any clarifications? I'll wait for 2 to 3 minutes. Okay, and then I'll proceed with the next topic. Then we'll go for fault diagnosis. Okay, I'll give you some case studies. Right? Anything that you want to interact? Just we'll have a break for 2 to 3 minutes.
So actually, that the interaction section will be at the end of the.
Okay, so okay,
That's
okay,
it.
right.
Thank you. Thanks.
Okay, then I'll proceed. So now, when you take the fault diagnosis, okay, in BLDC motors, okay, how it is done. So we have done a work for Hall sensor fault diagnosis. So we'll have a battery, okay, which is followed by a three-phase inverter, okay, which is given to a BLDC motor. Okay, the output from the inverter drives the BLDC motor. We have a current control. So this is generally a block diagram, a simple block diagram for BLDC motor, BLDC motor drive. So here, okay, what we have done is, okay, this is the structure. Either we can also go for a boost converter. Okay, depending upon the requirement, we can also go for a boost converter. So what we tend to do is, we tend to take the S transform analysis. Okay, why I say S transform? S transform is a time frequency transformation. Okay, it's a time frequency transformation to extract the features. Okay, to extract the features. So from this, okay, from these features, okay, we train a neural network for classification. We train a neural network for classification to be this, whether to be open circuit fault or single phase switch fault or double switch fault or short circuit fault. Like this, we tend to classify the different types of faults. Okay, so this is what we were aiming, right? So there are different time frequency transformation techniques. Either you can go for S transform, or you can go for wavelet transform, or you can go for Hilbert transform. Like this, you can have different transformation techniques, right? Each one has its own merits or demerits, right? We can either go for there is one more transform, okay, which we can call it as Hilbert transform as well. So that also you can go, right? So that is how it is done. So here, see here, we extract two features. Okay, we extract two features, F1 and F2, for classifying the fault, right? So one feature is what we call it as mean of the amplitude plot. Second, we call it as a standard deviation, right? So I assume that these are statistical values. Okay, mean and standard deviation. You can, in simple terms, I'll put it, these are all two values which represents mean and standard deviation, right? See here, under normal condition, okay, we are taking a Hall sensor fault. We all know that BLDC motor requires a Hall sensor. So under normal conditions, right? So what happens is, this is the normal excitation sequence, right? So 001 means we'll trigger the switches 5 and 4 for clock anti-clockwise direction. For clockwise rotation, we'll trigger 1 and 2. So these are all the Hall states. So this is the normal value, normal waveform for torque and speed. Okay, this is the normal value for current, normal waveform for the current. Now what we tend to introduce is, we will extract the features for normal condition. Okay, these are all the values for normal operating condition. We will extract the features. Now we introduce a fault in a Hall sensor. We assume that a Hall sensor is faulted. A Hall sensor is faulted. So when there is a fault in a Hall sensor, okay, we'll assume that there is a fault in a Hall sensor C. So when there is a fault in Hall sensor C, we see that this Hall sensor is not changing the value. Okay, when you see the previous case, okay, see the first three states were 0, 0, 0. The next three states were 1, 1, 1. This is the normal operating condition. So there is a change in the Hall sensor value. Now, when you see the Hall sensor values, see what happens. All the values are 0. It means that the state is not changing. The Hall values or Hall signals are not changing. So when the Hall signals are not changing, it means that there is a fault in Hall sensor C. There is a fault in Hall sensor C. So see what happens to the current. There is a variation in the current. There is a variation in the current with respect to the normal waveform. See, this is the normal waveform. Under normal condition, the current waveform. Okay, see the pattern. So here there is a change in the pattern. Okay, there is a change in the pattern. We observe a change in pattern because of the Hall sensor failure. So due to this, what will happen? The features, due to this, what will happen? The features that are extracted, changes. What happens? The features that are extracted changes. So what are the values? See here, the values are changing. So this indicates that there is a fault. Where there is a fault, this indicates that there is a fault in Hall sensor. There is a fault in Hall sensor C. There is a fault in Hall sensor C. Right? So these are all the values that we have taken. Similarly, if I say double Hall sensor failure, if there is a fault in two sensors, again see the value has increased. See, the value has increased. So from this, we can note that if these values are like this, right, we can know that there is a fault in double Hall sensor. Two Hall sensors are faulted. Right? Okay, so how will I do? First, what will I do? I'll initiate the closed loop speed control. I'll analyze the stator current waveform. I'll apply S transform. See here what I do. If the observed values are equal to the actual values, I'll check whether if the observed values are equal to the actual values. If it is not equal, okay, no, okay, right? So what happens if there is a fault? Okay, I'll have the features for fault condition. If the observed value matches with the actual features value under fault condition, then I'll identify the nature of fault and then I'll classify. Else, I'll again keep on implementing this particular algorithm. So this is how I classify whether there is a fault or not. So I'll have the feature values. If any one of the feature values matches with the single Hall sensor fault, what will happen? Okay, I'll say that there is a Hall sensor failure. So for that, what I require? I require data. So that is how I'll classify the fault. Okay, so this is again a diagram. I'll analyze the stator current. I'll do S transform analysis. From the S transform analysis, it will identify whether there is a single sensor Hall fault or whether there is a double sensor fault. It will say whether there is a single sensor fault or whether there is a double sensor fault. Okay, so this is how it is done, right? Okay, right. So now what will I do is I have made a MATLAB video presentation on how to classify, how to extract the features. Okay, I'll just share that particular presentation so that you can have a better idea on this. Okay, I'll stop sharing this. Okay, and I will share that particular window. Tell me
extract the features.
Are you able to hear the sound?
Using S transform
Yes, sir.
and Hilbert transform. So I'll take first a general sine wave and we will see how to extract the features of the sine wave, and then I'll take a sag wave, and then I'll take a swell, and I'll show how the features will vary. Once it is over, we'll proceed to how to extract the features in the same way as per the BLDC motor that we have used in an electric vehicle, or any motor you can use, any induction motor or any motor you can use the same procedure. So as I said in my lecture, whenever we want to identify a fault, there are two steps. The first step is we need to extract the features. The second step is we need to classify what kind of fault. So we are in the first stage. The first stage is feature extraction. So for this, first I'll take a simple sine wave. Okay, first I'll generate the sine wave for simplicity. These are all the initialization instructions. So what I give, I initialize the value of t. I give the limit for t. T varies from 0 to 0.5. Okay, this is the time interval for t. And I'll just say v is equal to 0.2 into sine omega t. So, and then I say the plot command. So when you see this, we will get a normal sine wave. So this is the waveform of a normal sine wave. Now, the algorithm that we are going to use should identify this as a sine wave. The algorithm that we are going to use should identify as a sine wave, this as a sine wave. So what we will do is, this is a time varying waveform, or we can say the waveform varies with respect to time. So we need to apply a transformation technique, and we need to extract the features that will characterize this waveform. We should get numerical values that will characterize the waveform. Okay, we can take the RMS value of this, but when we have more number of features or more number of waveforms, then RMS value might not be a good indicator. So we'll go for the transformation techniques, S transform, and we'll go for a Hilbert transform. We'll go for transformation techniques. So we'll see how to see or how to use the transformation technique. So I have stored the values in a variable called as v. Now I am going to apply. Now I'm going to apply an S transform. So to apply the S transform, okay, I have a pre-written program. I have a pre-written program. Just 1 minute, it will open. I have a pre-written program. See, the program is open here. So this program, okay, which is available in MATLAB, will give the S transform features. So for this, what is the input? The input is going to be my waveform. Here I have taken it as a sine waveform, right? And I need to extract the features. So this I have written a program called as MIET. Okay, you can have any name. So there are two programs. One we call it as a MIET, okay, which is used to extract the features. Okay, here I have written a subprogram. So what I do is I take the S matrix. ST stands for S matrix. T stands for time. F stands for frequency, and I give the name or the input value as V. V is my sine wave. So when I execute this particular program, it will in turn call this ST. It will in turn call this ST, and I'll get the features. So this F1, F2, F3, F4, F5, I have taken 20 features. We'll get the values of those 20 features. So that is the first step. So what is the first step? I'll give this program new ST. I'll give new ST. So when you see, this will take the S transform, and here we'll get the features. We'll get the F1, the F10, because it is arranged like this. Like this, I have initialized 20 features. I'm not going into the details of what features we have used. So I'm not going into those details. So these are all the values. So for example, if I take for a particular sine waveform, here the magnitude we have kept as only 0.2. The magnitude of sine wave we have kept as 0.2. If you see the plot of the waveform, you'll be able to see. So F1 value. So what is F1? F1 is a maximum of time amplitude plot. So S matrix will return both two values. One is time as well as frequency. So first four features represent the time amplitude plot, or we call it as a time maximum amplitude plot. So I'll write it here. I'll just for understanding purpose, I'll get write the value here. This is a normal waveform. Okay, I'll give the different magnitudes here. I'll say here 0.2, and here I'll say 1. Okay, 1 in the sense the magnitude is higher. So what is the value of F1? Here F1 is 0.1. How do we calculate the F1? We calculate F1 by applying S matrix from the S matrix. So F1 is 0.1. Like, okay, or we can also type it here, F1. Then F2. Okay, what is F2? F2 is 0.0995. Okay. Or I can say it is 0.1. F2 is 0.1. Okay, that is also 0.1. F3 is for some waveform the features might not change. F3 is again 0.1. Okay, that is why we take more number of features. Right, F4, I'll take F4 is almost equal to 0. So the first 4 features I'll take. If you want, you can also say F5. So like this, we extract the features for each and every waveform. So F5 is 0.5. So F5, I'll put it as 0.5. F5, I'll put it as 0.5. So this is for a normal waveform with amplitude 0.2. Now what will I do is, I'll clear this. Okay, now you can also get a normal waveform with a higher amplitude. So I'll just take this and I'll put it as 1. And I'll just say I'll just first plot it. I'll plot this waveform. So when you plot this waveform, so now we have a higher amplitude. So this is also a normal waveform. Right? Why we are doing this exercise is because it should differentiate the normal condition and maybe we can call it as a sag condition or a swell condition. So this is not a swell. So it is a normal waveform, okay, which is a sine waveform. So what will happen is, even for a normal waveform, when the amplitude varies, what will happen? The features values will vary. So that is why we take different waveform as inputs, okay, and we train the machine learning algorithm. So here again, for a normal waveform, I extract the value, I do the S matrix, and I calculate the value. See here now, for this is a normal waveform. Even though it is a normal waveform, the value of F is 0.5. F1 is 0.5. We'll see the value of F2. So F2 is also 0.5. F3 is 0.5. F4 is 0. Fi is 0.5. So these are all the values. So what does differentiating all these things are 0.5? Right. So how the machine learning algorithm will work? It will check whether if the values are in this particular range, then we can classify them as a normal condition. See here, it's all is 0.1. Fi is 0.5 for both the cases, whereas F1, F2, F3 values will change. So this is for one amplitude. I'll call it as a normal condition. Normal condition. So what are these things? These things are what we call it as features, which characterize the waveform. Now to make it more clear, what I'll do is I'll take a sag waveform. I'll take a sag waveform. So in a sag waveform, again I'll say, I'll first generate a sag. So this is the syntax for generating the sag, right? When you see the waveform, you'll be able to understand. So I'll generate a sag first. Let's say CLC. I'll generate a sag. Okay, so plot V. So I'll generate a sag. So see here it is, sorry, this is a swell, sorry. So this is a swell. If I want to have a sag, what I can do is this value of V, I'll just change it and I'll just change it as 1 minus. If I put 1 minus, it will be a sag. 1 plus, it will be a swell. So I'll say plot V. So we'll have a sag. So here the sag occurs here. Okay, sag occurs in this particular instant. Now this waveform has to be recognized as a sag waveform. So what will I do is I'll see what are the features for this sag waveform. I'll again say new ST. So it will calculate the values. So see here, we'll see 0.5. So I'll take it as a sag waveform. F1 value is 0.5, right? So I'll take F2. F2, see here, F2 is 0.3. F3 is 0.45. Now we can see the difference. F2 is what is the value? I'll just check it. So F2 is 0.3, F3 is 0.45, F2 is 0.3, F3 is 0.45. F4 is F4 is 0.07 and Fi is 0.3. So see here for a sag waveform, for a sag waveform, F4 is 0.07, it is 0.3. So see what happens for a sag waveform. In a sag waveform, what happens? The values changes. So this will characterize the waveform as a sag, right? Because there can be many sags, in the sense the amplitude can vary, the instant of time can vary. So we can have the sag occurring at different instants of time. So that is why we require a time frequency transformation. So the sag can occur anywhere in the start, anywhere in the middle, or it can occur anywhere. So we need to keep on continuously sampling the values, and we should extract the features. And based on the features, the machine learning algorithm will say whether it is a normal waveform or a sag waveform. Now I'll take one more example. I'll take a swell. As I said earlier, I'll just take a swell example. So I'll say clear all. The same thing I'll take. So I'll take a swell. So I'll generate a swell first. So I'll say plot V. So now see here, the same thing, the swell has been generated. Now for this, if I apply, we'll see what happens to the features. So we'll get the features. So see here, F1 is 0.7. So F1 is 0.7. F2 is 0.5. F3 is again 0.55. So 0.5, 0.55, 0.5. It is 0.55. And F4 is same value, and F 0.07, 0.3. So 0.07, and it is 0.3. So here there is a difference. Okay. So that is why we take more number of features. So what we do, what we have done, first we have done a S transform. And to that S transform, what we have done is we have extracted the features. We have first generated a waveform, and we have extracted the features. And we will see what are the features that will come for different waveforms. Likewise, we need to generate a data set. So this is one transformation technique, which we call it as S transform, which we call it as S transform or a Stockwell transform. So if you see this program, I'll take the S transform, and the value of S matrix will be stored in SD. And I do a calculation, which is mostly mathematics based calculation, and I extract the features. So what are features? Features are used to say what, or it is used to characterize the waveforms. Which are used to characterize the waveforms. Okay, so this is a set of program that it has been written, and features are extracted. I say here, for example, I have taken 20 features. Not all the 20 features will be required. You can optimize that as well. So that is one more separate part. So this is one part of it. There is one more time frequency transform, which we call it as a Hilbert transform. So that also we can use, right? So that also we can use. That I'll just say, so you have a sag waveform here. You have a sag waveform. I'll apply a value here. So again, I'll plot V. So we'll get the waveform. We'll get the swell waveform. Okay, we'll get the swell waveform. Now to apply a Hilbert transform, okay, what we can do is I'll just say S1, or I'll say H1 is equal to Hilbert of V. V is my waveform, Hilbert of. So see what happens, the Hilbert transformation will be generated. So what I need to do is I can, this consists of a complex value. So I can extract the real values. I'll say AB absolute of Hilbert of V. Right? I'll now say plot of H1. It's a plot. So see what happens when I plot it. So this will represent there is a swell here. See this portion, there is a swell. The other portions are normal at 1. So this is one thing that we call it as a Hilbert transform. So now how to characterize this? To characterize this, again I can take the features. I can say mean of H1. Mean of H1. So mean of H1 is 1.0597. So this is one technique. So what is the Hilbert? This we can extend. We can have some more features, and you can characterize the features corresponding to that particular wave. Now the same thing, we'll just take up one more example. I'll take a swell. Sorry, I'll take a sag. I have taken a swell now. Now I'll take a sag. So when I take a sag, I'll just say plot. I'll just give the value. I'll say plot of V. So now there is a sag waveform. So for this sag waveform, what I'll do is I'll take the Hilbert transform. Now I'll say plot of H1. So see here, there is a marked difference between those two waveforms. The first swell waveform, what we saw was there was a swell, but now here there is a sag. So there is a dip here. So there is a dip here, right? So it means that there is a variation here. Now, if I take a mean of this particular value, if I take mean of H1, so it will be different. It is only 0.9, indicating that there is a swell. Right? You can also make different instance of sag and swell. So here, the value that we have given is A is 0.4, 1 plus 0.4. It means that it will be 1.4. Here I will say it starts at 0.16 and it will end at 0.24. For example, I am saying. So I'll generate a different instant of swell. I'll say clear all, just to show the difference. Right? Since we saw the swell sag waveform, I'll just take it as a sag itself. Now I'll take plot of V. So when I take plot of V, see here now there is a variation in my instant where the sag occurs. So now if I take the Hilbert transform this, see what happens. I'll just take the Hilbert transform. I'll plot it. So when I plot this, see what happens. The instant will change. But we'll see what happens to the mean. We'll see what happens to the mean value. But the mean value also has changed a little bit. So depending upon the time at which the fault occurs and depending upon the magnitude of the fault, the features will vary. So the features are used to characterize the waveform, characterize each and every waveform. So this is the basic. So this is what we call it as a feature extraction. Now, when I give these features as input to my classification algorithm, we will be able to classify the nature of the waveform. We can say whether it is a sag, whether it is a swell, or whether it's an interruption. Like this, we can say. The same principle we are going to apply for a BLDC motor or for any motor. So what I have done is I have taken a MATLAB model, okay, which is already available. For simplicity, it is already available. I have taken the same reference, right? So this is the model available in MATLAB just to show how a fault can be created and how you can characterize the fault. So in a BLDC motor, I use an inverter, which is used to drive this BLDC motor. And these are all the measurement parameters. I have a Hall sensor, and a Hall sensor will be given to the gate signals, which will in turn trigger the gate pulses. It will trigger the gate of the inverter. So this is the normal flow. So I have a Hall sensor. Based on the Hall sensor, the triggering of pulses of the inverter is going to take place. So depending upon the speed reference that I give here, as per this particular example, the input voltage is varied, right? Or you can also have a PI controller and you can also do it. But here they have used a PI controller for the changing the source, but we do not usually do this. We'll sense the current and we'll just change the gate pulses here, right? So there is one method. But I have taken a model which is already available in MATLAB itself. So when you execute this is under normal condition. This is under where I have changed this. I'll just show. Yeah, this is compiling. Just a minute. So here I forgot to give one input. So we need to give that input. Okay, sampling time I have not given. So I'll give the sampling time TS as 5 e power minus 6. So now it will work. So I have given this as input. So we'll see the output waveforms. So when you see this is the speed, we have given speed as 3000. Sorry, I think I have not changed this here. 1 minute. So here to introduce fault, I have made a change. So I'll just remove that as well. So now it will work. So we'll see the normal operation. So when you see here, this is the stator current, back EMF, rotor speed, all these things we are sensing. And this is the normal current waveform. This is the normal current waveform for A phase. This is for B phase. And the other thing is for C phase. And we also get the torque and speed. The torque and speed. Right? This is the torque and speed. Okay. They have given a step input. Initial value is 0. The final value is 3. So that is why there is variation in torque. Right? So now we want to analyze some fault which is occurring in the inverter. So first we need to take this particular waveform and characterize the features for a normal operation. What are the features that are there for a normal operation? Only then we can characterize the fault. Right? I'll just enumerate the procedure. So this waveform, I have stored it as a variable. As a variable, I have stored as I1. The same procedure I am going to apply. That is why I explained the S transform previously. So now the variable is I1 here. What I do is I just see the value of I1. I1 is stored in I1.signals.value. I1.signals.value. So when you see this, there are totally 5,000 values here. There are totally how many values? 5,000 values here. So here, that is why sampling plays a very important role. So this has to be a continuous process wherein we need to sample the signals. I'll take first 1,000 values. So I'll say V is equal to I1 dot signals dot values of 1 is to 1,000. I'll take the first 1,000 values. Now I'll plot this V. Okay, I'll plot this V. So when you plot this V, I'll get this value. Okay, I'll just get this waveform. So what I'm going to do is I'll apply the S transform for this particular value. So I'll get the features. See, F1 is the value, F10, F2. So F2, I'll just take it. F2 is 1.3140. F3 is 1.3140. F4 is 0. F5 is 0.5. So like this, I take the values. This is for a normal waveform. Right? For a phase current A. Okay, you can also have for different phase current, you can get the values as well. Now suppose I am going to introduce a fault. Okay, for introducing a fault, you can make this as a individual switches and then you can also introduce, but I am giving a simple procedure. See here, I am giving 1 to where? To the first device. So the first device, what I'm going to do is I am removing the signal, and the first device, I am going to keep it permanently on. It is not going to be on off. It is going to be permanently on. Right? It's going to be permanently on. So now I'm going to simulate this. So when I simulate this, see the current characterization. So the current value will change because it's like I'm keeping it permanently on. It's like short circuit, right? So when I take this particular value of current, stator current, see what happens. I'll take the first 1,000 values again. I'll take the first 1,000 values. Now I'll take new ST. Okay, it is better to clear this and then you do it. I initialize first TS as 5 e power minus 6. I'll just run this. So this is under fault condition. So what I do here is I'll just take the value of V as 1000 values. I'll take new ST. So see what happens. So here, see here, the value of F1 is 18. So it has jumped to 18. So it means that there is a fault. And the fault can occur in one switch or the fault can occur in multiple switch as well. So that is why we go for machine learning algorithm and we go for more number of features to accurately classify the fault. Right. So here again, the value will see F2 is 18, F3 is 18, F5 is 0.5 because F5 does not change, F4 is again 0. So like this, each and every value is going to change here. So which will characterize the fault. One more thing I'll do here, instead of permanently turning on, I'll permanently turn off this. Right? It is like open circuit. So that switch will not be triggered at all. So what happens? See, this is the output. Now again, I'll repeat the same thing. What I do is, I'll take the, it's better to say run again. I'll just say clear all. I'll just say CLC. I'll just initialize TS. So now I'll run it again. So what will happen? I again take the first 2000 values. I'll take new ST. Now if you see the values is different. Now it has become 1.6186814. Similarly, F2 is again the same value. This is 0, F4 is 5. All the other values are same. Right. So depending upon the waveform, the features value will change or it will be same. So like this, what happens now? I have made an open circuit. So there is a distinction between a short circuit that is permanently making the switches on, permanently making it as an open circuit, and a normal condition. So what we need to do? We need to prepare a matrix like this, right? And it should have the waveforms at different time instance. One more thing is very important that we need to do is the fault can occur at any instant of time. So here I can couple a time and say that only during a particular time there is a fault. So for this, we can have a step waveform like this thing, and we can also say when it becomes 0 and when it becomes 1. Like this also you can say. You can give a step input and vary the time of instant of fault. So here we are assuming that the fault occurs directly when the motor starts itself, the fault occurs. But that might not be the case. It might be under normal operating condition, but after some time, what will happen? The fault might occur. So we need to take care of that condition as well. So a large database is required. Why a large database is required? Because the fault can occur at any instant of time, right? And a fault can occur in any particular phase, right? Or one phase or two phase, and the time can vary, and the load condition can also vary. So you need to incorporate the variations in load. You need to, because when there is a variation in load, the current waveform will change. Right? The current waveform will change. The speed value will change. So like this, you need to take the variations in the load as well, variations in the time as well, and then we need to vary the instant of fault, and then we need to generate a database. So if we have all combinations in the database, then the fault classification will be accurate. So what will we extract from here? We do different simulations and we incorporate different conditions of fault. And what database we take? We take a database which has features and which has a classification. This table we need to prepare. This table is very important. What does this table give? This table gives the relationship between the feature, the values, or we can say the features and the condition. Conditions in the sense a normal condition, a no fault condition, like this, the condition. So here you can incorporate, here I have taken only current. You can also have a speed waveform, right? You can also have a speed waveform, or you can also extract the values from torque as well. Suppose you want to have a vibration signal. So then you can also have a vibration signal as well. right? So you can add n number of variables, but all these variables are time varying. So since we are operating with a time varying variable, we require a particular transformation technique to extract the features. It need not be a S transform. It need not be a S transform. So as we discussed, okay, you can also take a Hilbert transform as well. Okay, you can also take a Hilbert transform as well. So I'll say TS here just to illustrate this. I'll run this program. Okay, you can also apply a Hilbert transform, and from the Hilbert transform also you can take the values. You can take the values. So see, I'll again say the values here. I'll say the command. I'll say the command h1 is equal to Hilbert of absolute of v. Right. So I'll say plot of v. So this will give a plot indicating that it is a decreasing one, because I have made it as 0, because the value we have given at the gate is 0. Now we can also take the Hilbert transform. So what we can do is we can take the Hilbert value, mean of h1. So mean of h1 will be 0. Now if I introduce it as a permanent 1, okay, then if I keep it as 1 itself, so that again there might be a change. So there is a variation here. So what I do here is, it is better to clear it. I'll say clear all. I'll initialize this, and now I'll again simulate it just for. See what I'm doing? I'm again taking the first 1000 values and Hilbert, and I'll say plot. So this, see, the way there is a change in the nature of the waveform because it is permanently 1. And now if I take the mean of Hilbert transform, the value is changed. So likewise, for different fault conditions, you can extract the features, and these features will form an input to your classification algorithm. This is the first part. So I have explained how to extract the features using the feature extraction technique, namely time transformation technique, time frequency transformation technique, namely S transform and Hilbert transform. Okay, so participants, I thought I would share that particular presentation so that you'll be able to understand it easily, right? So coming back to the summary. Okay, so I have come to the end of the session. So there are 2 steps. Okay, first step is we should extract the features. Second step is we should classify them. For classification, okay, as I said, you can apply any of the machine learning classifiers. Okay, so that if there is time, I will take it up as next part. Okay, because there is a time constraint. I thought I would explain it, so that is why I prepared a video so that you will be able to understand it. So the machine learning algorithm based classification will form the second part. So this is how you can diagnose the fault in electric vehicle drives. Okay, so thank you for the opportunity. Okay, hope this session was useful. If there are any clarifications, we can discuss. Thank you.
Thank you, sir.
Thank you.
Is there any questions? Please, you can unmute your mic now.
Good evening, sir. This is Shinoy. Am I audible, sir?
Yes, sir. Yes, sir.
Actually, sir, this was a wonderful session. Only thing is, you were talking about Hilbert and S transform.
Yes, sir.
This is new to me. Is this anything to do with our Fourier transform, in which we will characterize the signal.
The same sort of thing, sir. It is next step in case it's an advancement with respect to Fourier transform, sir, so that you can have a better classification with respect to noise as well. So it is a time frequency transform.
Okay, so one more thing is you were telling that for the diagnosis, we will be running a model parallel to the actual system.
Yes, sir.
Where will we compare the actual as well as the model?
Yes,
so,
sir.
The model should, if the model should be exactly replicating the actual phenomena, the model should be very complex, right, sir?
Yes, sir. That is why we don't go for that. We go for the sensor based, like this type of approach. First, we have a simulation model. From that, we extract the features and train it in real time.
Okay, sir. So second thing is, suppose we are avoiding the model based, means model is not the, as you told, from the data set, we are classifying the means errors, and you're shown with the SAG and means 12 waveforms.
Yes, sir.
But the time period, if it is like whatever time, the data cannot be so continuous, we will be crunching the data for say
No, that
one.
is why sampling plays an important role, sir. Your question is understandable. So that is why what we tend to do is we sample it. We sample every 1,000 values, and for every 1,000 values, we take the values. We apply these techniques.
Okay, you mean this as the 1,000 values we
1,000 in the
expect.
sense that it depends on the sampling time or sampling frequency, I can say. You can have a sampling frequency. This is a continuous process.
Okay, sir.
But
So
for extracting the features, we are assuming that we have the fault occur in a predetermined time. Okay, but what we tend to do is in a normal situation or in a real life situation, we sample it continuously for the sampling frequency of 2 kilohertz or 3 kilohertz or 5 kilohertz. And for every 5 kilohertz, what we do, we tend to apply this S transform, take the features, check it. Likewise, it is a continuous process. This will be running in the controller parallelly in addition to your normal control output algorithm.
okay,
You
sir.
understand? You understand
Yes, sir,
what I said?
definitely. It was very much insight, sir. So
Okay.
one more thing, like you showed that 5 parameters of the waveform.
Yes, sir.
Usually in the EV application also,
Yes, sir.
currently which we are pursuing, like many motor means many vehicle manufacturers are realizing the vehicles.
Yes, sir.
So how many parameters, like as you told, F1 to F5, how many parameters will be there, like in the F series itself, how many parameters we'll be looking for get an accurate
So what
value?
we will tend to do is, sir, we tend to take some 20 to 25 parameters, and then we will analyze those parameters and come to a small number of parameters that will really characterize the fault. We don't require all the 20 parameters. 5 or 6 parameters is enough. So we need to optimize those parameters and see which are more relevant for classification. Like this, we need to do analysis from the features.
Okay, so one more doubt that is related to the research work currently going in this area, sir. What is
Yes,
the
sir.
future of research work currently moving in this area, sir?
They tend to apply image processing techniques for the waveform. That is one thing, academic side. Okay,
Okay, sir.
another thing is in battery management system, there is a lot of scope for machine learning algorithm. There is a lot of data. They send it to through IoT, they send it to cloud, they take it to the cloud, do the algorithm and see whether the battery is under normal condition or not. Right, and they apply these machine learning algorithms, or what we call it as deep learning techniques, for fault classification. But for everything, there are two types of data that is required. One, we need to have a real time vehicle and take the data from there. We need to create a fault, or we need to create a simulation setup in MATLAB and see whether the experimental results match with the simulation result, and then we should extract the data from the simulation model. So modeling is also very important. As we said, mathematical modeling of a drive is very important, because only then we can extract the data. So in modeling as well, the work is proceeding. So these are all the areas where the research work is in progress.
Thank you, sir. Thank you for that information, sir.
Thank you, sir.
Any other doubts from any other participant? Yesterday's video is been uploaded in YouTube and the link is been provided, and today's session will also be posted.
Ashish Patel, sir. If you have any question, please post it, sir.
You can even put it in chat box.
Good evening.
Good evening, sir.
Sir, in one of the slide that of fault diagnosis,
Yes, sir.
you have mentioned about the sensors.
Yes, sir.
I mean, providing a sensor and thereby extracting the data and fault diagnosis there later.
Yes,
But
sir.
sir, let us say in case, let us say we have the SRM type of drives,
Yes, sir.
switch reluctance motor. There are, I mean, like physically for rotor position sensing, the sensors are already there.
Yes, sir.
So can we, I mean, like utilize those physical sensors itself for just achieving the
No,
fault analysis?
no, that is for only position sensing. There
Okay.
might be a fault in those sensors as well.
Okay.
So we need to have either current sensor, voltage sensors. That is
Okay,
for
sir.
non-invasive type.
Right, sir.
For invasive type, we should go for either vibration signals or thermal sensors for detecting the
Okay.
type of fault. So
Right,
rotor
sir.
position
Right, sir.
sensor will give the information about rotor position, not about
Only.
the
Okay.
fault.
Yes, sir. Right, sir. Right, sir. Right, sir. Right, sir. Thank you so much, sir.
Thank you,
Thank you.
sir. Thank you.
Thank you.
Any more questions?
Participants, if you have any question, please post at the chat box also.
Okay, you can always mail me balajim@sn.edu.in. Okay, hope I have given some input such that you can proceed your research work in this particular area. So thank you. I once again thank the management of Jerusalem College of Engineering for giving me this opportunity to interact with the learned audience. And I'd like to thank Dr. Vinod, Mala ma'am, and Arul sir for inviting me to this particular session. Okay, thank you,
Thank you, sir.
participants, thank you all, thank you all.
Sir,
Have a
thank you,
nice day.
sir. Thank you for accepting our invitation and giving
Thank
this
you,
wonderful session. Thank you, sir.
thank you, Vinod.
Thank you, sir.
Thank you.
Participant, please fill the feedback form before 7:45. The feedback form will be closed by exactly 7:45. Thank you.
Participants, after filling the feedback, you can leave. Ma'am, you can stop the recording, ma'am.
Okay, sir.
Thank you, ma'am. Thank you.